We are now discussing about string matching problem. In the previous two lectures, we have seen a basic naive algorithm for string matching and also the Rabin-Karp string matching algorithm. Today, we are going to see how we can use finite automata for getting an efficient string matching algorithm. So, the topic for today is string matching by finite automata. Recall the string matching problem. Given a text and a pattern as input, the problem is to find all the occurrences of the pattern in the text. And if you recall, the result is obtained as a set of valid shifts. For example, here 3 is a valid shift because after the index 3 in the text, the next 3 characters are matching with the pattern. And similarly, you can see that 8 is a valid shift because after the index 8, the next 3 characters match with the 3 characters of the pattern. And one more valid shift is there, which is 12. And why is it a valid shift? If you look at the next 3 simples after 12, it is a pattern. So, the occurrences of the pattern are represented with valid shifts, and here 3, 8 and 12 are valid shifts. Now, we can see how we can utilize finite state automata for finding valid shifts or solving the string matching problem. So, for that we need to know what is a finite state automaton. Let us try to understand what it is using a simple example. This is what is shown is a state transition system, and if you look at the components of a finite state automaton, the first component is the finite set of states, capital Q. In this example, you have 2 states P and Q, and in general there could be finitely many states. And the second component is the finite set of input alphabets. In this example, sigma is set AB, the input impulse. And third component is a state known as the start state. It must be an element of Q and called the start state. In this example, it is P. This is how a start state is represented in the figure by an arrow not originating from any other state. And now the fourth component is what is called the transition function. What is it saying? If you are in a state, then when you read an input symbol, what is the next state? That is what a finite a transition function in a finite state automaton defines. In this example, if you are in the state P and reading the input A, it says you move to state Q, P on A going to Q, and P on a B coming back to P itself. So, remaining in the state P, you are reading the input B. Now, from the state Q also you have transitions defined for A and B. And for a deterministic finite state automaton, it is required to have exactly one transition defined for every input symbol from a state, and the last component is a subset of states known as finite states or good states. It is a subset of states, and in the given example state q is final. It could be any subset. So in the figure it is shown by a shaded circle. So basically a finite state automaton is a quintuple: finite set of states, finite set of input symbols or alphabets, one of the state known as the start state, transition function, one transition for every symbol from a state, exactly one transition, and a set of finite states. That is it. Now try to understand how a finite state automaton works. Given an input which is a string on the input alphabet set, it starts its computation in the start state, in this particular case at P. And what is it doing? Until there are input symbols to be processed, based on the current state and the current input symbol, change the state as defined by the transition function. So this is what it do. It starts with the start state of the automaton, and depending on the current state and current input symbol, it makes a state change. That is what it is doing. And the input may be having finitely many symbols, and when it completes reading the input, it accepts the input if the computation entered in a final state. So when you finish reading the input, suppose the machine entered in a final state, the input is said to be accepted, otherwise it is rejected. So that is the semantics or the way it functions. An example can make it more clear. Suppose the input is AB. So where you start? You start with the start state. You are here, and what is the next thing? Until you finish reading the input, based on the current state and the current input symbol, change the state as defined by the transition function. So what is the first input symbol? A. So which asks you to change to Q. So that is what you do. So A is read off. Now you are in the state Q, and the next input symbol is B. So what you do? You stay back. Now you are in state Q and you are getting a small a. What you do? You go through this edge and come to the state P. That is what you do. Now you are in the state P and you are reading small b as the input, so you will stay back. So in this case, you finished reading your input and you finished in a non-final state. This is the only final state. So the input by definition is rejected, because you entered the processing of that input in a non-final state. Another example is this, and you can trace the execution of the automaton. You can see that in this particular case it is ABAA, ABAA. You will end up in the state Q and you will accept. Basically this is what is a finite state automaton. And it is not difficult to see that this example automaton accepts a string over AB if that string contains odd number of A's. That you can verify offline. Now let us see how can you use finite state automata for solving the string matching problem. Now suppose this is the input given to you. You want to find valid shifts, and assume that someone is giving you a finite state automaton, and how you can construct this automaton is a different question that you will see in the next lecture. And suppose you are given this automaton, what you can do is you can just read the input text. You do not have to worry about the pattern which is actually represented as an automaton. So, you start in the start state. What is the first input symbol? Small a. What do? You move to this state. Now, you are in this state, you are reading small a. So, you are coming back along this loop. So, staying back and reading that symbol. Now, you are here and reading the next symbol as small b. What you do? Move along this edge and come to this state. Yeah, you are here and now you are going to read a small a. You will go back to this state. What is next? You are here reading a b. So, now you are going right and coming to this state. Now, you are in this state and you are reading small b. What you are asked to do? You are asked to move to this state. Now, you are coming to a final state. Then what you can do is you can print the present index, which is 6, minus the length of the pattern 3, 6 minus 3, which is 3, as a valid shift. So, you printed 3 as a valid shift. Later you can verify whether it is correct or not. This is the processing, as simple as this. Now, we continue. You are in this state, you are reading a small a. So, coming to this state. Now, what is the next input symbol? Small b. Going right to this state. Now, what is next? Small a. Going back to this state. What is next? Small b, taking you to the next state in the right. Now, you are processing a small b, coming again to the final state. So, what do you have to do? Print the index, which is now 11, minus 3, which is 8, as a valid shift. Continue. What is the next symbol? Small b, which will take you back to the initial state. Next is small a, which is taking you to the next state in the right. What is next? It is a small b, which is taking you along this edge, and you are now in this state. Now, you can see that only one more input symbol, and which is a b. So, you are moving right, landing up again in a final state. So, by following the same procedure, now you have to print index, which is 15, minus 3, which is 12, as a valid shift. So, if you do this, the algorithm is printing 3, 8 and 12 as valid shifts, and the algorithm is making use of finite state automaton, which is given by someone else. And now you can see that 1 is a valid 3 is a valid shift, because after 3 you have the pattern occurring, and 8 is a valid shift because immediately after 8 you have the pattern. Similarly 12. So, this is a wonderful idea, but how to get this finite state automaton is a question that we shall address in the next lecture. Now, we see that finite state automata enables us to find all valid shifts in the order of number of elements in the input. So, this is a linear time algorithm once this automaton is given. And if you recall the complexity of the naive algorithm and the Ravenkarp algorithm, in the worst case it was m into n minus m plus 1, and when the size of pattern is as large as the input, then it is quadratic, but here it is linear. But it remains us to see how can you automatically construct this automaton from a pattern, and that is the agenda for the next lecture. And today we are coming to the last slide of this lecture, where I am giving you a homework exercise where you try to come up with an automaton which will accept a string over AB if and only if that string contains this as a substring. Try to come up with an automaton. After you draw the automaton, run this input, run that automaton on this input, and also consider some strings which can be accepted and some other strings which needs to be rejected, and see whether you are getting a right automaton or not. In the next lecture, we shall see how you can do it automatically. Today, we have seen how one can use finite state automata in getting a linear time algorithm for solving the string matching problem. So, today we assumed that we will get an automaton representing the pattern, then just running the automaton on the input string enables you to find all the valid shifts. So, it remains us to see how can we construct that automaton which is known as the prefix automaton from a given pattern, and that is the topic for the next lecture, which is addressed by the Knuth-Morris-Pratt algorithm for string matching, that we shall see in the next class. Thank you.